So we're going to talk a little bit about a topic that you probably have heard about, software supply chain security. I was supposed to have a demo, and that demo was supposed to work. But I also was on vacation, and I just came back Sunday and straight to here. So I didn't really have time to check it. So we'll assume the demo works. You will have to trust me that it actually works. But we'll simulate that it works, right? So we'll talk a little bit about software supply chain security, generally speaking, and like why I think that everybody should be mindful of what they're doing, especially if you're a developer. My name is Abdel. I'm a developer advocate at Google. I co-host a podcast called the Kubernetes Podcast by Google. I don't know if anybody here is a listener. All right, I'll give you 5 minutes. I'm just messing up with you. That's my Twitter. I mostly work on subjects related to Kubernetes itself. But security is one of my, let's say, favorite topics. And I work on security in the non-standard way, in the sense that I don't really care too much about vulnerability and research and all this stuff. Or I do read about this stuff, but it's mostly about the overall approach to security in software development, generally speaking. So before we get going, I have just one, how many people have heard of software supply chain security before? Raise your hand. OK, cool. How many people actually understand what it means? OK, few people. Well, good. So I'll help you figure it out, right? If we take the word software supply chain security, we can actually split it into three sections. Software, right, which is what everybody does. That's why we're here, right? Supply chain, which is just pretty much a fancy term to say CI/CD, and security. And the term software supply chain security literally means the security of how we supply software, or in other terms, the security of how we get software from where it's developed to where it's running. That's basically what the idea is about, right? Supply chain is a marketing term. It doesn't really mean much. It was borrowed from supply chain as a term of how you get food from farm to table. But generally speaking, whenever you hear supply chain, just think about it as CI/CD. And in the context of software supply chain security, we don't only care about how do we secure the software we're writing itself, but we also care about the software used to supply your software. Because the reality is, as a developer, you write code, but in order to get that code built, tested, and shipped to production, you use somebody else's code, right? If you are using Jenkins or whatever tool you use for CI, that's code as well, right? And how safe or secure that code is also important. So as a developer, you start with some source code, and you use some dependencies. You put these things together into a build system. You build your software. And then the result is essentially a binary, or maybe a library, or a piece of software, right? The reality is, and that's something that I don't know how many people actually realize, is that your dependencies are actually built the same way. It's sort of like a vicious cyclic circle. Like your dependencies probably have their own supply chain method to get them to you so you can use them. Your libraries are also following the same exact method where somebody writes code, built it, and then ship it. Just instead of shipping a binary, they're actually shipping a library, right? And this sort of cyclical kind of vicious circle in terms of dependencies is what makes, in my opinion, shipping software today quite scary. Because the reality is, as a developer, you're probably not writing pretty much everything from scratch. You are relying on somebody else's code that you're importing into your own code to be able to build your own features, right? So just some numbers to get you a little bit scared, I guess. I guess that, I'm not going to go too much into the numbers, but I want to tell you a few stories, because I think that storytelling is one of my favorite things about doing public speaking. Everybody remembers Log4j, right? Or Log4Shell, right? SolarWinds is actually the name of a company that was impacted by a software supply chain security type attack a few years ago. It's an American company that supplies monitoring software, and one of their customers is a company called Continental Pipeline, which is the company that supplies the east coast of America with oil. So they basically ship not oil as the the crude oil, but like the results, like petrol, right? And so they were impacted, and so their pipelines stopped working, which means they stopped supplying the east coast of the entire United States with diesel and petrol. And the result was that actually people got scared, and there was like lines for 2 hours to be able to fuel cars, right? And this is just an example of how this kind of problems in software could have potentially real-life ramifications or consequences on actual humans. It used to be that we hear about security and we hear that somebody hacked somebody or somebody leaked some data, and that's all kind of virtual because it's in the internet and no one cares, unless your data got leaked. But what's happening in reality these days is that these kind of problems are having real-life consequences on humans. And I'm going to talk about a very specific example that happened close to where I live in Sweden, and there is an example that happened very close to Sweden. But just the idea is, this is just another example to show that in other real-life examples, you are probably not even building the software you're using. You're using third-party software. You're relying on somebody else's piece of code to be able to conduct your business. And if that person or group of people are not careful about what they're doing, they could have a sort of snowball effect where one vulnerability that is that makes one operator vulnerable could have, snowball effect on a bunch of their customers or their partners. Let me show you the example I want to show earlier. Kaseya. So in Sweden, we have a very big supermarket chain. I'm not going to mention the name. They have about 700 stores in the entire country. And this happened in 2022, I think, if I remember correctly, where they basically had to close almost 700 of their stores from 24 hours to 6 days. To give you an idea, this is not your typical Rewe in Germany. This is actually your typical small supermarkets that exist in the middle of nowhere. And if you ever get to visit Sweden, one thing that is interesting about Sweden as a country is that if you take Stockholm as a city and you go north of Stockholm, there is a city called Uppsala. If you draw a line over Uppsala, 90% of people live south of that line. So 10% of the population that lives in the north of the country, which is pretty much the rest of the country, rely on this particular supermarket to get their stuff because they have small stores all over the country. And so what happened to them is that they use a piece of software, which is an IT management software to manage their computers, but they actually subcontract the management of these things to an intermediary. So there is the supermarket company. They subcontract some of their IT stuff to one company, which uses another company's piece of software. And it's the small player in this example on the right side, the off-the-shelf software that got impacted, which then a patch was shipped, which the IT company installed in the supermarket system, and the snowball effect I talked about, right? So one company got impacted another company, impacted another company. And for basically what happened in this example is that the supermarket chain had about, for 2 months, a backdoor that was basically leaking some data to some remote server somewhere. So they had people uploading how much ice cream people bought and how much French fries people bought and stuff like that. Like, it was not really that bad because there was no financial information leaked, but and no PII. But this is just an example of how bad these things could be. And the reason why this kind of things happen is because the way we ship software, again, back to the initial idea, is extremely complex. So there are multiple ways in which things can go wrong, right? You could simply start with a vulnerable package. You download something, you don't really pay too much attention. It has a vulnerability, you import it, you use it, boom, you have a vulnerability in your end results. As far as I remember, as far as I can tell personally, the earliest example of this particular problem was actually a security researcher that was demonstrating how vulnerability in open source could impact people. And they did that, the person did that by gaining committer access to Homebrew, right? So everybody uses Homebrew on Mac. So they gained committer access to Homebrew. And they demonstrated that by gaining committer access, they could basically commit code into Homebrew that could be vulnerable and then end up with everybody having that vulnerability on their computers, right? And this was a while ago, even before we were even talking about master branch protection in GitHub, where you have to have code reviews before you could merge code. So basically, if you don't have master branch protection in GitHub, anybody who has committer access can just commit and merge code into the main branch, right? And that, therefore, ship vulnerabilities. You could also have your own. You could have vulnerabilities that basically doesn't show if you do some sort of like static code analysis or you test your code before you ship it to production. But once that package gets executed, it downloads some sort of remote package and becomes vulnerable. So sort of like a timing bomb kind of situation, right? So it looks legitimate on the surface, but once it's executed, then it becomes vulnerable. You could have vulnerable source code. This is very, very common. Like, people write bad code for many reasons, not only because people are stupid, but people do write bad code. You wake up in the morning, you have a bad day, your coffee was not good, and you write bad code. That could happen. Some people might argue that that's called job security, but, whatever. Or my favorite example is, and this is actually, you remember earlier when I talked about the fact that you write your own software, but you use somebody else's software to build your software. And if that third-party software is vulnerable, that could cause a problem. Well, pretty much everybody uses CI, which you don't write code for, right? All your CI tools are third-party CI tools. How many people here write their own CI tools? Like develop their own CI tools from scratch? Okay, 0. Good. So that was my assumption. So I mean, if that CI tool has problems, you could end up with problems. I think I don't want to mention names. There is a very famous managed CI company. I don't know if they're a partner, by the way. I should not probably talk about them if they're a partner. There is a very famous managed CI company that got hacked, I think, 2 years ago. It was either last year or the year before. And it happened around Christmas time, where they basically leaked their own AWS keys. So they didn't leak their customers' AWS keys. They leaked their own AWS keys to the internet. And yeah, then it took them 2 weeks, and then they notified everybody to tell them, please rotate your keys. So there's just an example of, how shit can go wrong. My favorite example, this is the last thing to like, I say scare you between quotes, but actually more to make you aware. How many people have heard of this XZ outbreach? Okay, few of you. If you've been living under a rock for the last year, XZ is a compression library in SSH, right? And it's a very important compression library because one of the things you could do with SSH is you could copy files, right? SCP, copy files over SSH. And when you use the SCP command line, it uses SSH under the hood. And SSH has this XZ compression library, which compresses files. And it's a very fascinating story if you really read the details. But basically, whoever put this vulnerability into XZ was a malicious, intentional thing that started back in 2021. And it started in the open source. So somebody started contributing to SSH or to XZ, sorry, the library, and then became eventually a committer and started by removing some guardrails into GitHub that prevented people from committing bad code, and then eventually committed a vulnerability. And this was discovered by somebody at Microsoft who was debugging a SQL server and noticed that whenever they execute SSH, it uses a lot of CPU cycles, and then figured out that actually when you are using the SSH SCP command line, it just uploads stuff to some sort of remote server somewhere, right? So just an example of how things can go wrong. So now the question is, what now, right? So I've been talking about how things can go wrong for a while. How can we solve these problems? Well, this is probably my least favorite way of describing it, but there are two main methods by which things can be made better, I would say. One of them is zero trust. So zero trust is a word which is borrowed from networking, which essentially means in the process of supplying software to production, you don't trust that every single step is executed by a legitimate user. You verify that every single step is executed by a legitimate user, right? And I'm going to show you a very concrete example. That was supposed to be my demo, which is not working. But I'll try to show you a very concrete example of what that actually means. Shift left is borrowed from DevOps, which essentially means making developers aware of what they're doing, not making them responsible, making them aware, giving them the tools that allows them to verify that the libraries they're downloading are good, that the code they're writing is good, et cetera, et cetera. So how do we do this? There is an effort called Sigstore. It's a combination of multiple companies that got together. I created a project called Sigstore. The website is sigstore.dev. And they basically do three main things. They write software to sign and verify software. And they write also software to monitor. I'm going to show you examples concretely. So these are what we call the Sigstore components. Some of the components you probably don't know, but the one I wanted to demonstrate today was cosign. So cosign is a command line tool that allows you to sign and verify OCI images, so open container initiatives. So any image which is OCI compatible can be signed, verified with cosign, the command line. Then the signature and the verification of this, or the signature at least to that image, could be made public in what we call a ledger, which in this case is a ledger called Recore. So Recore is both an open ledger, which you can consult on recore.sigstore.dev. You can go there, and then you can look for a container image, and it will tell you if it was signed, who signed it, blah, blah, blah. And you even have the public key if you want to verify the signature. But also, it's an open source software, so you can host your own instance of Recore. So if you're writing private software, if you're writing code that you don't want to make public, you can actually host your own Recore instance. And you can make that a ledger in which you can put signature. You can walk in, guys, if you want to take a seat. I don't think you will want to stand for a very long time. Just come in. They also have a bunch of other components like OpenID Connect and the Certificate Authority. And I'm going to explain all of that in a bit. What does that mean? But basically, the entire story or the entire TLDR of Sigstore components is that you have software that you can use to verify or sign and verify the signature of your own software. They also have a framework called SLSA. It's written SLSA, which stands for Security Levels of Software Artifacts. It took me 2 years to master how to say that, but we pronounce it SLSA. And what it is, essentially, it's a checklist type framework, or basically a verification type framework, where you have a bunch of best practices that you can follow in implementing your own CI process. Not your CI software, but the CI process itself. How do you ship code? And depending on which kind of best practices your CI or your supply chain meets, you can meet level 1, level 2, level 3, or level 4. I'm going to show you an example here. This is what SLSA looks like, kind of. This is actually a pretty old screenshot. There is a new version of the framework that was released. But we can take an example here of SLSA level 3. And you can see in SLSA level 3, we have code versioning, Git basically. We have verified history. Verified history basically means that if you have ever used, how many people here know Git sign? Do you know a tool called Git sign? Few of you, right? Cool. So if you don't know, Git sign is actually a tool that allows you to sign your own commits. So you can verify that the commit is coming from a legitimate user. So you can sign the commit itself, right? Then you have retention, and then you have a bunch of other description, like your build system is scripted, it's ephemeral, which means basically you don't execute 2 builds in the same worker, blah, blah, blah. So those are just some of the examples of what SLSA could look like. I'm not going to go too much into details about this, but the last thing I want to mention is that there are actually 2 of probably the most common or the most famous open source projects that have been verified that their supply chain process follows SLSA level 3, Prometheus and Argo. So Prometheus and Argo both have been audited, and they both follow SLSA level 3 in terms of compliance for how they supply the software itself, right? So in terms of how they verify the software, how they verify the builds, et cetera, et cetera. So basically, according to Sigstore, so this is Sigstore version of how supply chain should look like. So instead of having that simple, write code, build code, test code, ship code, you basically have the same thing, but you just add verification at every step. And this is zero trust in an example. So you as a developer, you build an artifact. You could request a certificate from the Felucio. So Felucio is Sigstore own certificate authority. But you can have your own certificate authority. You can actually use whatever KMS, key management system you have or whatever. And then you use that to sign the artifact. Then you publish the artifact itself. And then you publish the signature to Recore. So this is this thing here, the transparency log. So you add to the transparency log a log that says this piece of software have been signed by X, right? And then as an end user, you can basically either look up in Recore to verify if a dependency have been signed properly, or you could just download the artifact and download the key and verify the signature yourself. This diagram is a little bit too complicated. So I have a very simple, stupid way of explaining this. How many of you have before downloaded the CLI and downloaded the SHA-256 file associated with the CLI and used the SHA-256 command line to verify the signature of that CLI? All right, what the rest of you, what are you doing? Just kidding. So this is just a complicated way of describing the same idea, right? So you download something, you don't know if that thing was, issued by somebody you trust. So you download a piece of code that allows you to verify it. And so this is just the same exact idea as a basic, but slightly more complicated with signatures and certificates and stuff like that. The last piece of this puzzle, in terms of software supply chain security, is something called SBOM, or software bill of material. So the way I like to describe SBOM, again, in a very stupid way, I like to use 5-year-old metaphors, is SBOM to software is a recipe to a dish. It's essentially the list of ingredients that have been used to build a specific dish. The only difference is that when it comes to food, one recipe can allow you to produce multiple versions of the same dish. When it comes to software, one SBOM is always associated with one artifact. And if a single thing changes in the artifact, the SBOM should change. So the SBOM is essentially the list of dependencies, the list of libraries, the list of files. When it comes into containers, SBOM is usually files inside the container that container is made out of. And that's usually attached to the artifact as metadata. So you could verify, you could use the SBOM to, when it comes back, you could use the SBOM. Theoretically, you could even use the SBOM to reverse engineer or rebuild the artifact from the dependencies inside the SBOM. When it comes into container, it's pretty easy. There are actually 2 formats for SBOM, Cyclone DX and SPDX. That's just like the format of the file. There are multiple ways you can create an SBOM. Docker has a command line to create SBOMs, Docker SBOM essentially. But there is also other piece of software. Sift has one, SYFT. There are multiple types. They all follow the same standard format, and they basically contain inside of it the package name, the package information, the file, whatever licensing comes out of like whatever license that piece of software have been supplied as, etc., etc. Why do I mention this? Why do we care? Why should we care? Well, that's because one of the reasons is because SBOM is going to become very important because the EU, the European Union, actually passed a law which will go into effect next year that forces certain companies operating in certain sectors to produce and store SBOM for a certain amount of time and to supply it to regulators in case they're asked. So if the company operates in the context of like defense, finance, healthcare, these kind of things, the law is called NIST, NIST, and I think it's NIST2. You can go read about it, but essentially it's essentially like GDPR, but for software, right? So if your company operates in certain sectors, and when you go read about it, basically it sounds to me like pretty much everyone, because it's like transport, energy, finance, healthcare, defense, which pretty much is all sectors, right? So like if you operate in these sectors, you probably will have to do that. So before I finish and I show you what was supposed to be my demo, SBOM and SLSA are complementary to each other. They're not mutually exclusive and they're not mutually inclusive, in the sense that you don't have to adopt all of it and you don't have to adopt any of it. Security, I always describe security as basically an onion. It's a bunch of layers that you have to add depending on what are you trying to solve and how much complexity do you want to carry and how much technical depth you carry. So you don't go, oh, we're going to do salsa. Let's start on the 1st of January to do salsa, and then 31st of December, done, we're good. Let's not talk about it anymore. That's not how it works. It's a continuous process by which you're continuously evaluating what you are doing, are you doing the right thing, and how do you be more safe. I don't like to use the word more secure, but more safe. So I'm going to show you what was supposed to be my demo again, but it's not working. Sorry about that, but I'll show you very simple. So there is actually let me see. Yeah, so you could use cosign itself to verify images. So this is an example where you could So you could like build a container image essentially, and then just use cosign to sign it. Yeah, this is an example. So you do a cosign sign. I can show you another example here that I have in my was supposed to be my demo, but whatever. Give me a second here. Yeah, so this is an example where you could verify, sign a container image. So cosign sign, and then it takes as an input a key. In this example, I am using a key coming from Google Cloud, GCP, KMS, but it actually supports AWS, it supports Azure. It's pretty cloud agnostic. It supports a lot of other tools. So you can give it as an input, like a key, and the container image itself that you want to sign. And then it will generate the signature of that container image, and then attach the signature as metadata to the image. So it will add another layer to the image, and that layer will contain the actual signature. And then if you, of course, if the container image changes, you re-sign it again, and then it gets signed again. Then to verify it, you can use the cosign verify command line. So this is the example I talked about of zero trust, where between stages, between building, testing, and running your code, you could sign, verify, and make sure that the container image is coming from the right source, right? So this command here will just give you an output to say if that container image have been signed using that key, particular key, and it will produce an exit code 0 if this verification was successful, exit code non-zero if the verification was not successful. This is a more complex example where you can actually even attach SBOM, so you can generate the software bill of material as metadata, attach it to the image, and then use cosign to sign the SBOM itself. So you could sign even the file containing the SBOM information, just to verify that that SBOM information was coming from the right source. And then if you're on Kubernetes, you could use a policy controller that cosign has. So you deploy the policy controller. You create a policy called cluster image policy, in which you could basically say all the images, so that's the globe star star, have to be signed or have to be verified against this key. And this policy plus this label here on a namespace would basically make it such a way that if you're trying to deploy an image and that image have not been signed by the key you specified, the image deployment will be rejected, right? So it's a policy controller. So it will allow you to basically make sure that the image signature that you have specified have been honored or have been, honored. That's the word I was looking for. So yeah, so that's basically, I think that's it I have. I think so. And yeah, so the TLDR is sign your images, verify that they are signed, and make sure that you are downloading stuff from sources you trust. Thank you very much.
Thank you very much, Abdel. Very interesting talk, by the way. Thank you.
Thank you.
We don't have any question on the Slido, at least for now. Again, please, if you have any questions, we use a Slido app that you can get access to via the CDS app. So download the app and ask your question through the Slido. That will also help us streamlining the experience. But I have two for you. The first is, so for someone who just jumped into this security area, there's a lot of tools and concepts to handle and to make it, let's say, work perfectly. What would be your best advice to start this journey?
The first start would be to sign and verify your images. I mean, that's like, in my opinion, very low effort. Just make sure that as your container images are actually moving between your stages in your build pipeline, you can sign and verify them, just like easy. The second thing is vulnerability scanning. Pretty straightforward. All cloud providers today have some sort of vulnerability scanning. If you don't use cloud for whatever reason, there are a lot of open source tools. Like Docker has a tool for doing vulnerability scanning. Projects Graphias, which is open source, also have tools for doing vulnerability scanning. Yeah, so that would be my advice. Start there, and then there is, like, as I said, it's an onion thing. You can just build layers on top.
We had one question coming up, which is pretty cool. Thank you for the one who asked it. How do you prevent false positive in your SBOM for libraries you don't use? Your Ubuntu base image may contain a vulnerability OpenSSL library not used, for example.
I didn't get the question. I have to How do you prevent false positive in your SBOM libraries you don't use? Example, your Ubuntu base image might contain a vulnerability OpenSSL library not used. Ah, very good question. In that case, you should probably be using Ubuntu to start with. Like my advice in this case is just to use like minimalist images. Don't use images that contains piece of software that you don't actually need. The easiest is to use what do we call them? Distroless images. So use an image that doesn't contain an entire Linux distribution. The easiest answer to this actual particular question would be to build containers from scratch. The reality is that no one is doing that, but just use minimalistic images or as minimalistic as possible, and then you can avoid false positives. That would be the easiest way of describing it. The longer answer to that question would be that the problem with security is that false positives could actually be problematic in the sense that if you actually know that inside your container image there is a library that your software is not using, so you basically explicitly ignore it, right? You see that your vulnerability tool is reporting this is a vulnerability, but you ignore it, then you can easily fall into what I call ignore fatigue or pager fatigue, which is you keep ignoring stuff up to the point where you ignore actual things that might slip under the hood. So my advice is just prevent that by just using images that doesn't contain things you don't use, essentially.
Okay, we have 3 more questions. How does signing an image would prevent me from something like the XZ issue?
When someone backed into a broken software? Yeah. That's a very good question. You don't have to be sorry, by the way. It doesn't. Sign-in is not, the purpose of sign-in is not to prevent vulnerabilities caused by open source backdoors. The purpose of sign-in is verifying that as your image is moving between the steps of your supply chain, the image itself has not been modified. So sign-in solves one problem. It doesn't solve all the problems, right?
Does SLSA with Zero Trust require verifiable builds, or how are they related?
Yes. So in the SLSA level 3, verifiable builds are a step. It's like a requirement to be able to be SLSA level 3 compliant. So yes. But with Zero Trust, well, yes. I mean, with the purpose of Zero Trust, again, is to make sure that your container image is signed across the entire process. So verifiable build is a way of making sure that the build have been verified properly. So sign-in and Zero Trust is part of that.
Thank you very much. And one last question. Does it mean that proprietary software is more secure than open source alternatives, since the lacking opacity makes attacks more difficult?
No, because even proprietary software is built with open source. The reality is that your company that makes your proprietary software is also relying on open source software. And that was the purpose of the title, is the relying or our dependency on open source is scary, is because everybody uses open source. Unless your software that you are using, your third-party closed source software, has 100% guarantee that they are building everything from scratch themselves, right? Which I have very high doubt that they're doing. Unless that's the case, I don't think that it's actually more. I would say that it's even, in this particular case, it would be even less secure, because I would trust if there is no if there is no transparency in how that software have been built.
Thank you very much, Abdel, for this talk. Can I get a big round of applause for Abdel, please?